Welcome to session 5 of module 1 on need for big data analytics in smart grid. In the previous session, we saw the basics of big data analytics, and in this session, we will cover fitting function to data points, classification and regression. Fitting function to a data point. Initially, if you see, from smart grid, we have collected a huge amount of data that is coming at the X end, and at the Y output we need some applications like visualization or classification or prediction. For this we need to build a model. Given a data set D, the objective is to learn the relationship between the feature and the target. First is classification. Classification is a supervised machine learning technique. It uses the object characteristics to identify which class or category it belongs to. Example, a new mail that you can either classify them as spam or not a spam, or a patient need to be diagnosed for a deadly disease. He may have or he may not have that disease, or a short circuit fault had occurred or not. So first is the binary classification. Here you can see two sets of data. One is a blue set and another one is a red set. Now a new point comes in, and now you have to classify this X whether it belongs to the blue class or the red class. So generally when we ask, what we do is we just try to find the centroid of these classes. So if you find the centroid of the blue class is CB and the centroid of the red class is CR. And now we will find the distance between them. And if the distance, that is XCB, is greater than XCR, then we say that new point belongs to the red class. And at the same time, if the distance, that is XCB, is less than XCR, then we say that the new point belongs to the B class. In case the density of the two classes are not matching, in that case the centroid method will fail. So in that case what we need to find is, we have to find the standard deviation of these classes and divide those from the distance what we have already found. So dx comma cb, from that divide by sigma, that is the standard deviation, that will give you a distance. Similarly for the other class. So then here in this case it will give you a right answer. Even the centroid method will fail for a case which is shown here, where there are blue class which is split into two groups. So in such a case we have to go for clustering, which is an unsupervised learning technique. So one more technique for classification is draw a line, a linear line between these two classes and separate them. For example, here a line is drawn, x2 minus m x1 minus c is equal to 0, which will classify this unknown point x. So in this case the unknown point goes to the blue class, and that is said to be the hard classification. But many a times there is a doubt prevailing whether it belongs to the red class or not. So in that case, when a machine has a doubt, we can go for soft classification. In soft classification, a probability function is added. You can use in sigmoidal function, where here it will predict that the new point is 60% belonging to the blue class and 40% belonging to the red class. So here let us, for soft classification, let us introduce a sigmoidal function. So the probability function p is equal to 1 divided by 1 plus exponential of minus h, and the straight line equation is given by h is equal to x2 minus m x1 minus c. In case if the h value is very large, then you can see that it is in the blue class, and if the h value is very less, then it comes in the red class. And here for doing soft classification, let us first assume the h value to be 0 in the probability function. So when h is 0, what happens is the exponential term there will be 1. Okay, so 1 divided by 2, that is 0.5. So the probability of the new point is 50% it may go into the blue group, or 50% it may even go into the red group. That is, this point is on the line. The second case, let us imagine that the h value is a very large value and it is a positive value. In that case, the exponential term will be a very small term, so that whole 1 plus exponential term will become 1. So 1 by 1 is 1. In the sense, new x value is being classified into the blue class, 100% classified into the blue class. Let us take the third case, when the h value is a negative value and it is a very large negative value. So when h is a negative value, so minus h is already there, and again the value is negative, so minus into minus it becomes a plus, which is a very high value. Exponential of a very high value there will give you a very large value. So let us just imagine that term had gone to infinite. So in that case, your probability is 0, in the sense it doesn't belong to the blue class, it entirely goes into the red class. So with the h value, you can easily classify them into different classes. So this is how we do classification with sigmoidal function. Now let us imagine the data points as given in figure. So in this case, a linearly separable model cannot be made. Here you can see, when I make a linear straight line, some of the points are crossing the line. Let us take an example of a classification of a deadly disease like cancer. If a person is having cancer and it is predicting that he is not having cancer, then it is a very dangerous situation. So we have to avoid that. In such cases, we go for nonlinear classification. In nonlinear classification, you can see here we draw multiple lines and separate them. So for nonlinear classification, we have to go for neural network. So here this is the neural network model, and here you can see that you have the input nodes, that is x1 and x2, they are the input data or the input nodes, and you have the output, which is the h star and v star, that is the output node, and in between you have the hidden layers where you have number of nodes. So the number of nodes depend on how many lines are required for this nonlinear classification. So here each node is given by you can have a polynomial equation or a straight line equation with the sigmoidal function is also given, so that how much percent it belongs to a particular class can be easily classified. So using this neural network, you can do nonlinear classification. And say in this neural network, you give a bias. The bias will shift this line up or down, and when you are changing the weight, it will just change the slope of the line. So accordingly, you can do the classification. So now let us see the same illustration of neural network using a simulation. So here you can see two inputs, x1 and x2, and this is the data which we have taken. So there are two sets of data, one is a blue group and one is a orange group, and you have to classify them. So we can, I've used a sigmoidal function and learning rate is 0.03 and 2 neurons in one hidden layer. So one hidden layer I have and 2 neurons I have taken, and output also there are 2 neurons. So now when I run this, automatically you can see it's a linear classification and it classifies that into 2 group. So at the same time, now when the data is non-linear, so let us try this. When the data is non-linear and when you run it, it takes a long time and it will not be able to classify this. Though it tries to two sides, it will try to classify, but again it will not be able to classify it properly. So in this case, let me try to increase the number of neurons. So accordingly, say I am just trying to increase the number of neurons and I am trying to run the same program. So now it takes little time, so it will be able to classify this blue class and the orange class. So it will take little time, but at the end it will change the weight accordingly. All the weights will be changed and automatically it will start classifying it. So here you can see it's trying to identify the blue point. So here I have used 3 neurons in the hidden layer. So almost it has classified the thing. So here you can see 3 lines are there. So like 1, 2 and 3. So here when I put 3 neurons, automatically it is able to identify the center portion. So many times we have a doubt how many neurons to add. It depends on the complexity of our problem. So next we move on to regression. In regression, it is used for mostly prediction purpose. For example, let us see some points are given here, the blue points, and these, just let us imagine that these are the points taken from some sensor and we don't know what is the characteristics of that sensor. But here, the side itself, we can just see that it is similar to that of a sine wave. So in case now we want to make a model and fit with this, we just go for a polynomial curve fitting. So here the polynomial equation is given y of x comma w is equal to w naught plus w1x plus w2x squared plus so on until degree m. When your m value is 0, you can see y of x comma w is equal to w naught. So our model which we are fitting is this red color line and it doesn't fit with our original data. So that is m is equal to 0. It's only a constant straight line. When m is equal to 1, that is y of x comma w is equal to w naught plus w1x, you can see again it's a straight line with a slope. The slope depends on the w1 value. And next again I am increasing the order of the system. So m is equal to 3. In this case almost it has fitted with the sine wave. And the next case is a case which is shown here with m is equal to 9. It perfectly fits all the point. All the blue points are touched with this model. So it is perfectly fitting. So in this case now we are just going to see the training error. And let us imagine a point which is shown by a blue star here, which is a point which is already existing. That is the training data. The blue circles are shown. I am taking one of the same point. So which is shown here. And for degree m is equal to 0, in the table you can see the training data error is 0.9. The arrowhead is shown here. The value is 0.9. Similarly, when m is equal to 1, our value between this training data and our fitting model is 0.7 is the error. And when again the degree is increasing, m is equal to 3, you can see the error has reduced, it is 0.1. And when m is equal to 9, it is a perfect fit and your error is 0. Now what I am going to do, I am going to take an unknown point. That is, I have to predict it. So in that case, let me take an unknown point in this sine model. So that is given by a black star here. In that case, the test point error, if you see with the red line, it is 0.2 in the first case when m is equal to 0. When m is equal to 1, it is almost 0.1 from the red line. And when m is equal to 3, you can see it is a perfect fit, 0. But when m is equal to 9, you can see the error is increasing, it is 0.3. So now we can come to a conclusion that our model, what we have designed, though it is a perfect fit, it is overfitting. So sometimes for an unknown point, it will not be able to predict. So optimal degree is also a very important factor while we are choosing the model. So these are the different ways by which we develop a model. With this, we come to the end of this session, and in this session we saw some of the basics of machine learning algorithms. We saw the classification, then we saw the regression models. Thank you.